Up until now, we've been estimating the value of a definite integral, in other words, the area under the curve between 2 points, using rectangular or trapezoidal approximations. But as you might expect, there is a way to get this area exactly. So recall that the area that we're looking for is calculated by the definite integral, a to b, of g prime of x dx. And this refers back to this graph of this function, g prime. This happens to be the rate at which a pump is pumping water, and the units are gallons per minute. Now, we can think about this as approximately an infinite sum of gallons per minute, some quantity in gallons per minute, okay, which is the g prime part, times minutes. And so we could go through the math and come up with some numbers and some answers here, but the important thing I want to show you right here is that if we go through this calculation on the units, we find that the result is gallons. And so, as we've already seen, this quantity really represents the change in the number of gallons from time A to time B. And we can see on this graph on the right here that we're going to be plotting the number of gallons, and we see that this is going to be related to the rate of change of the gallons in the integral. And so right now I have A equals to B, time A equals time B, and I have 0 gallons at this point in time that have been pumped by the pump. If I move B and increase the amount of time that I'm looking at this change, and let's just drop this at time equals 2, I have 9.06 gallons. That's the area under this curve. Okay, gallons per minute times minutes, and the actual area under this curve is 9.06. Over here, as I move the time B farther along, I trace out the graph of G. And I see that from time 0 up to time 2, that the amount of water that's been pumped is delta G, which is this height right here, which is the area, 9.06 gallons. And if I look on this graph here and see where this ends up, that looks pretty reasonable, 9.06 gallons. As I move along and increase B, of course I get more gallons. Now you notice that delta G is increasing, but since the rate is slowing down, it's increasing at a slower rate. And so we go out here maybe to 8 minutes, and we see 27.53 gallons. That's this difference right here. 27.3 is right about in this area here. And so the area under the graph gives us the change in the height of this graph, the change in the amount of this graph, going from the rate of change to the quantity itself. Now, suppose I started measuring at time equals 2. So at time equals 2, in fact, let me back this up right here. Right now, I have 0 gallons pumped. Okay, so ignore this part of the graph just for a second here. What this is telling me is that the amount of volume change, the amount of water pumped from time A until time B is 0. Okay, now I'm going to move B again, and you'll see that I'm still tracing along this curve. And so if I go out between 2 minutes, which is my starting point, and 4 minutes, which is my ending point, I've pumped 7.42 gallons, which is right at this point. Now, this is telling me how much water I've pumped. It's not telling me how much is actually in the tank. I'm starting at 0 when I start my clock at point A, and I'm finishing up 2 seconds later and figuring out how much is pumped only in those 2 seconds. I might be concerned with how much water is actually in the tank. And so what I need to know is if I'm starting my measurement of the change in the volume at time equals A, which is 2 in this case, then I need to know how much is in the tank at this time A. If there happens to be nothing in the tank at this point, then the change in the tank will be the actual volume. But suppose that at time 2 I have 20 gallons in the tank. So I can set an initial value of volume G sub A, so the amount of gallons, number of gallons in the tank at time A, in this case to 20. Notice, however, that the 7.42 gallons has not changed. In other words, between times A and B, I'm still pumping the same amount. So even though I'm starting at 20, all that affects is my ending point. It does not affect the amount here. And so what this means is that in order to calculate this 7.42 here, all I need to do is find the difference here. It doesn't matter how much water is in the tank to begin with. And so what I see is that this delta G right here, delta G, is equal to the number of gallons at time B minus the number of gallons at time A. That's really our definition of delta. So the number of gallons at time B, which is 4, is this Y value. And the number of gallons at time A, which is 2, is this Y value, which is 20 in this case. The difference is 7.42, and that is delta G. So making the substitution, if I know that this is equal to this, then I get the result that the integral of my rate of change from A to B is equal to the quantity at time B minus the quantity at time A. And this is how you evaluate definite integrals. Okay, so let's take a look at this. We can erase this stuff. Let's take a look at this in a little bit more general terms. And what this is saying is that the evaluation part of the fundamental theorem of calculus tells us that if we take the integral from A to B of any function f of x dx, the way we evaluate that is to calculate the difference of the endpoints of the antiderivative. In this case, the derivative of big F is little f, or if you like, the antiderivative of little f is big F. And normally when I write an antiderivative, I have to put a plus c, but you'll see that if we do this, I'll get f of b plus c minus f of a plus c. And the c would have to be the same because we're dealing with the same antiderivative function. And so you'll notice that the plus c will cancel out with the minus c, giving me the formula that I've already written. And so it really doesn't matter what the value of c is. And if we think about this value of c, what that really is this. It's the initial value, if you will. And you notice that if I change that, no matter what value that is, it does not affect the difference, which is the amount of area. In other words, changing this graph by shifting it up and down does not change its derivative, and therefore does not change the area under the graph.